Thank you so much. I will say that it's an immense pleasure to be here after these past difficult years. And I must even say that I am enjoying being the sort of jet-lagged speaker giving the talk on the first day of the conference, something that I never particularly care for, but now I do. So some good consequences of these past few years. So the title of my talk is self-explanatory. So let me just sort of say that it's a work that I've been doing with a bunch of colleagues from Lyon. Zubair was a student with me, now he's in Pakistan. My colleagues Oran Azo and Emmanuel Lévesque, close to me. Bernard Melich and Christian, somewhere here, yeah, were sort of very, very great collaborators. And I'm also very happy to sort of acknowledge that Jennifer Yuha, who was a postdoc with me, is a person who sort of introduced me to that subject. Okay, so clouds. So we heard about clouds this morning. So the one I'm specifically interested in are cold clouds. By cold, I mean temperature clouds in which the temperature goes below zero, which you need to be high enough, and because of the gradient of temperature at 300-ish, 3,000-ish kilometers, 3,000-ish meters, you'll be crossing zero, and so between when the temperature is between 0 and -40, liquid becomes metastable. And you have the stable phase, which is solid, and further higher up, it's 100% solid. So then the question is that, so you have possible coexistence of these crystals and liquid droplets. Okay, so and of course, so when you look at what you can have in terms of ice crystal, it's a zoo. You can have lots and lots of shapes and forms, etc. So I'll be much more modest and focus on these little crystals here, which are about 300 microns, a third of a millimeter, and which occur and which are very flat with this sort of nice hexagonal shape, which occurs in a range of temperature between -20 and -10. So i.e. in the zone where there are both water and liquid and solid. Okay, so these things, so of course we're talking about the very anisotropic objects. So being anisotropic, well, there may have some particular orientation with respect to the vertical. And so there is some sort of a relatively well-documented phenomenon called light pillar. So that's happening typically when you have some very quiet environment, so no fluid motion. And then what seems to be happening is that your crystals effectively are horizontal. And so then you have these optical effects, and then you have formation of these things here. That's sort of amusing curiosity. So it sort of tells you already there is some orientation. But of course, what could happen is that if there is motion, well, then motion, the turbulence will potentially randomize everything. And the question we'd be asking is, well, how much orientation is there left when it starts blowing and you start having this isotropization effect? That is some not only a question of academic interest, but that also impacts the reflection properties of the crystals, which has in itself a number of consequences for the reflection of radiation, etc. The albedo, which, as you know, is, clouds are one of the nasty things which are not very well parameterized for models, and, all these things are important. Okay, so now the little cartoon I will be leading with is the following one. So that's one of these storm, cumulonimbus storm cloud. So here what's happening is that the nucleation is happening in the sort of warm part of the cloud where temperature is above zero. And then you have this sort of a very strong updrafts, which are taking the nucleated droplets and sort of bringing them at a very high altitude. And then, so you're very high, and the thing starts settling. And effectively, the two things I want to bring your attention to. Wait. Well, it's interesting. Okay. Well, sorry, there's supposed to be some color, but it's too pale. So I want to sort of point to this possibility of aggregation of crystals here, and also of the interaction between crystals and little droplets as they settle. So effectively, well, so this thing, you guys should be in color, and that's what I will be mostly discussing.
It shows up over here.
It does? Oh, yeah, that's right. Okay, thanks. Okay, so yeah, so it was I wasn't looking it up. Okay, so so when there's a problem, of course, we don't do the full problem, well, for reasons that are simple to explain. So here is what we do. So in terms of the flow, well, we know that actually it was discussed this morning that there will be stratification and all sorts of things. Never mind that. I'll just take so the simplest possible, conceptually simplest possible turbulent flow, i.e. homogeneous isotropic. Clearly, that's an assumption. And then, so I was showing this sort of a nice shape, which is already pretty simple, but it's not simple enough. So I will just replace this by a prolate ellipsoid, but an oblate ellipsoid, i.e. some object of resolution. We saw the large distance here and the very small one, the perpendicular, and that's typically what I will do. Beta as a ratio I'll take of 0 to 10 to minus 2. Okay, so then comes something that I will be dwelling with for a couple of minutes. So I will assume that there's a small particle Reynolds number. By particle Reynolds number, I mean the difference between the velocity of the particles and the difference of the fluid at the same position multiplied by A and U, so that's a decent Reynolds number. And I'll be discussing cases where that number is small. Now, so that sort of an invitation to consider, well, if it's small, take it all the way to 0. I mean, take it to extremely, extremely small. That's sort of an invitation to try what's known as Stokes approximation, i.e. just drop anything but viscosity. And that, well, that's some sort of the simplest thing you can do, but, one of the organizers over here once drew my attention to the fact that he was very suspicious, and he was basically right. Which as I will be explaining now. So, okay, so I will not discuss the force because the force is completely okay. The things that sort of are causing problem are the rotational degrees of freedom. So, well, what you have to do is we're effectively doing Newton mechanics, so we write, the force equal mass acceleration, and, rotation times moment of inertia is equal to torque. Well, the torque, so there is one part which you can obtain by sort of solving Stokes' equation and follow Mr. Jeffrey, who sort of figured out what it was, and that's sort of the object of that form. Then, okay, so that part is kind of boring. It's just that we don't do the problem in a Galilean frame, therefore we have to pay a price, and that's the price. And then there are possibly corrections. So, but notice that here the sort of the torque coming from the Stokes approximation has only here the velocity gradient, knows only about the velocity gradient, the strain and vorticity, and the axis of the angular rotation of the thing. So that's okay. So yeah, so that's what I was saying. And okay, so fine. So that's just an observation. So what is the effect of TI? So TI. So what we take is, so people have worked out for these kind of particles the corrections in a systematic expansion in the particle Reynolds number. So I was taking a Reynolds particle equals 0. Now let's try to be a little bit more sophisticated and introduce corrections. So the correction typically goes like that. So W would be the settling velocity, A would be the size, and sine 2 phi would be effectively the angle between the normal to my object and the gravity, direction of gravity. So that's what it is. Now, you see very well that, in fact, there will be two positions of equilibrium. One will be like this, and one which will be like this, which will effectively cancel the sinus 2 phi. One happens to be stable, the other one happens to be unstable, and the one which is stable is that one. Which is good, because otherwise I would have a serious problem to explain these sort of light pillar things that I was mentioning. So that's just what I was saying. So the notion is that, well, if I don't keep that one, if I don't keep this correction, and if I insist on the Reynolds, particle Reynolds number equals 0, then I'm in trouble. Okay, so now let's sort of do some things which looks completely trivial. Let's estimate the ratio between the torque due to these corrections and the torque due to torque, the term due to Stokes. Well, it should be a no-brainer in principle, because that one was obtained. No, the correction is a correction. So in principle, in normal circumstances, you would expect that this guy will be typically proportional to the particle Reynolds number, because that's sort of obtained by some sort of a systematic expansion in the particle Reynolds number. However, the catch here is that we're comparing apple and oranges. So that one doesn't know about velocity. It only knows about velocity gradient, and that one knows about the velocities. So therefore, the estimate, the expectation that that thing is small, in fact, turns out to be irrelevant. So if I sort of work it in detail, what I find is this: effectively, that the setting velocity squared divided by mu times the velocity gradient. And if I estimate what it is at high Reynolds number, I can re-express that as Ws over U0, so that's the setting velocity divided by the fluctuation, squared times Reynolds of the flow to 1/2. Now, large Reynolds number means that is large, so the possibility that this is small comes only if that is very small. But if that is very small, it means that effectively there is no setting velocity. So if there is anything of interest happening at large Ws over U0, which will be breaking the symmetry and possibly isotropizing things, it's only at large R when Ti gets large. And therefore, if we want to, if there is any bias in orientation, it will be imposed by Ti and not by T Stokes. Okay, so then we do numerics. Okay, so that's some sort of a boring table full of nitty-gritty. So let me just sort of outline 3 lines. Okay, so please look at that one, because my color comes here. I was just outlining this dissipation one, and here we varied a little bit the aspect ratio of these of the crystals and the size of the droplets. Okay, so statistics orientation. So it's effectively the notion is that it's as you would have guessed, when the turbulence intensity increases, well, then you effectively allow yourself to destroy any possible orientation. So that's clearly showing here why I'm plotting this variation here of this angle as a function of epsilon, and some so relatively straightforward to explain value of effect of beta, of the size of the crystal. Okay, so in fact, we can do in fact here much better than just numerics. We can actually sort of write some little model which we can solve. That's the work done in principle with Christian. Okay, so what, well, when all dust settles, you realize that the problem depends effectively on 2 essential parameters. One is the Stokes number of the particle, and the other one is the settling number, which effectively is a ratio of the settling velocity divided by the Kolmogorov velocity. Okay, lo and behold, you can solve the thing and effectively estimate the variance of the fluctuation as a function of the settling number and Stokes number. So that's the final result. So blue means that there is actually very little fluctuation, and yellow means that the thing is completely disoriented. Okay, so but that's what is possibly more useful if you want to do clouds, etc., would be that picture here, which is effectively the same, but I drew here effectively the lines corresponding to increasing turbulence intensity, and here increasing size of the crystals. So effectively, we can map things out and in fact compare this prediction with what I was showing before, and lo and behold, that works. Okay, so in the few minutes that I've left, so let me sort of briefly tell you about collision of droplets. Oh, I'm sorry, of ice crystals here. Well, so yeah, mistake here. So those I'm talking about that process here. Okay, so we can measure what is called the collision kernel here, which just is sort of a proportionality constant of the number of collision between time, volume, and number of particles. And you see, well, that sort of seems to increase with epsilon, with the turbulence intensity, but it has some relatively complicated dependence on the various parameters. And to cut a long story short, the reason why it's complicated is because, in fact, you have several mechanisms of collision which are interacting together. So the first one would be what Safman and Turner discovered, namely that turbulence can effectively bring particles together just by the velocity gradient. So, and that comes with some prediction. Another one comes from the fact that if you're settling with that orientation, you're settling slower than if you're settling with this orientation. So that gives rise to a differential settling. So a particle which is coming like this can collide with a particle like that underneath, and that's effectively this mechanism. And the third one was discovered by Grisha Falkovich and Bernard and Michael Wilkinson, and that's called caustics of slings. And that is due to the fact that particles don't quite follow the flow, inertial particles don't quite follow the flows, and that sort of gives rise possibly to an increased collision rate. And that you can effectively represent here so here it's mostly Safman-Turner when the crystals are extremely well oriented. So here there is enough disorientation, so you can have some differential settling, and above here it's effectively caustics driven. Okay, and so briefly in 1 minute or so, I'll just flash the result, right? Okay, so now I'm doing this one, so this rhyming, and so I'll just sort of effectively be showing just a couple of transparencies. So so happens that if you do the problem as we do it, that thing seems to care remarkably little about the turbulence intensity. So these things are effectively constant here. So only this one picks up a little bit. So there are different values of beta, and that's this particular droplet size. And so here, what's happening here is that effectively, the reason why it's almost constant is because all these things are driven by the velocity difference between the settling crystals and the particle underneath. So effectively, this sort of simple, you have this very simple picture of a kinetic theory where one particle will settle and catches everything underneath. So that's effectively what happens. And only here you start seeing a little bit of the effect of turbulence, which goes with actually some experiments from the group in Mainz. Okay, so I'll skip that. And that's my conclusion. I'm probably 1 minute too much, so I'll just slide.
Thank you very much. So the diagram that you showed with the orientation as a function of the Stokes number and the Sverdrup number, that was for one particular aspect ratio of the particle.
No. Okay. I mean, yes and no. You're right. Very good. So let's see. Let me see. Here, there was this mysterious parameter which I didn't introduce. So this parameter effectively relates to the coefficients that are entering the equation of motion for the ellipsoids. What happens is that for beta sufficiently small, and 10 minus 2 is already sufficiently small, these guys don't vary anymore. So that's why effectively, so that would work for the small beta I'm working with. Yeah. If you were to do prolate, that would be a different game. Okay. But for for the oblate I was working with, that's okay.
All right. Okay, thank you. More questions? Yes, please. Do you want to step up to the microphone? Yes.
Pedantic. Sorry about that. Okay, so thinking about so is there a nematic ordering in this problem, like an effective nematic ordering, if you can define?
Well, I mean, it's well, in the sense that the things are aligned. That's what you mean.
No, but you have a phase transition from an aligned to a, or you don't go in that tumbling regime?
No, I mean, that would be what it is. So effectively you have some sort of a continuous, okay, so if you take the order parameter as your delta phi, your relative, the variance of your orientation fluctuation, that sort of thing varies perfectly continuously. There is no, I mean, not that we could identify, nothing that we could identify.
So is it correct that in small Reynolds like approximations,
yes,
you don't get a tumbling orbit at all?
That would be harder and harder, because we would be, so that's that small Reynolds number. I mean, that small turbulence intensity. So, zero Reynolds number would mean that, you push the Reynolds number all the way down. So you go to here, and, so then of course, what's happening is that, what you'd expect. So that effectively the restoring force will make you horizontal, and if you sort of put less and less restoring force, you'll be more and more horizontal. So that's effectively what's going on here as you diminish the turbulence intensity. So that one is falsifiable. I mean, that one. So if some people have some measurement and they can tell me, well, you're out of your mind or you're okay.
Hi, so I have a question. Did you consider the hydrodynamic impact of the collisions?
Okay. No, I'm sorry. Yeah, I should have said. That's what's called ghost approximation. Yes, we are not at this level of sophistication. So at the moment, we're just sort of asking, when do these guys come together? That's all. Okay. Your questions, of course, is high in our mind, but we haven't done it. Yes.
Yeah, and the second question is so the less dependence of the collision rate between caused by the eddy dissipation rate. So does it mean that we can apply some constant collision rate for the not constant, like the sedimentation velocity dependent collision rate for those?
You need that one?
Yeah, this one.
Okay, it's actually, okay, so, I put up that diagram and say, well, careful, it's remarkably constant here, but if you start looking a little bit more deeper, and, if you go to higher turbulence intensity, well, no, effectively, well, you're comparing what you would expect by just comparing sort of the settling velocity of the two objects, and, for which you can just instantaneously estimate that object. You're comparing it with what the turbulence would do. So here it so happens that that one effectively the turbulence does very little. That one, which I sort of flashed very quickly, you see, so for 3 of them it's okay, but for 1 of them it's not okay at all. And that's just because in that particular case, the velocity difference between the two objects was actually very small. And then what sort of brings them together is turbulence per se. I mean, turbulence is no longer some decoration. You cannot just ignore it or sort of pretend that you didn't notice. So for that one, you have sort of you'd have to sort of discuss what are the expected settling velocities. If they are sufficiently large that and you can estimate what would be the collision velocity due to turbulence, by some back of the envelope thing, and just compare. And sort of whether that will stay constant or not, it will depend on that.
Good. Do we have one final question? Ray? Yes?
Just a quick question. Speaking of settling velocities, I mean, is there a change in the story of preferential sweeping and loitering and things like that? Is this something that comes into it?
We stumbled into some preferential concentration in the sense of maxi here. Because so effectively the velocity of the settling is g tau, give or take, plus some possible corrections due to what you inherit from the fluid velocity, and so it depends where the particles go in the flow. And so in that particular case, where you have disks, if you wish, and droplets, when they have the same velocity or very comparable velocity, it may mean different things because the settling velocity, the UE, the sort of contribution due to preferential concentration, may not be different and may actually play tricks on us, which. Yeah, so it should be coming, but yeah.
He was looking at settling of Saharan dust particles, so they're non-spherical.
Yes.
And the removal rates of these dust particles from the atmosphere were totally inconsistent.
Yeah. So okay. So we got here some. I mean, so here I don't. Okay, I knew that time would be an issue, so I didn't want to dwell on that one. But so we did run into some inconsistency, which we lifted by sort of understanding that preferential concentration, in the sense of maxi, not just the how do you call it, clustering, but the fact that particles would explore different parts of the flow. Right, whatever it comes, but the drops don't do the same as the disks, and so that can actually give you trouble. I mean, force you to think for a couple of weeks.
All right, I'm afraid we have to stop here, and of course you're welcome to continue the discussion during the coffee break. That brings us, so thank you very much again.